So to introduce Stuart, Marsh briefly, leads a highly talented structural engineering team at SOM's London office to develop and deliver innovative structural designs for a wide variety of projects throughout the UK, Europe, and further abroad. With an ever-increasing focus on carbon-efficient designs throughout his 30-year career, Stuart's diverse project history includes a mixture of high-quality commercial, residential, academic, and cultural developments, along with sensibly designed adaptive reuse and specialist artistic installations. So with that, the floor is yours, Stuart. I'm very excited to see your glass structure.
Thank you very much. What a fantastic start. Thank you very much, Philippe, and thanks to BE-AM for inviting SOM this year. We have a project that we're going to talk to you about called the Glass Vault. It's a little bit different, I guess, to direct additive manufacturing, but I think you'll find that there's some synergies. So without further ado, my name is Stuart Marsh. I'm a senior structural engineer in the SOM London office. I'm here actually in place of Alessandro Bigini, who is currently asleep in San Francisco and who was due to speak this morning, but I've taken over. Both he and I were heavily involved with this project, so I'm not some interloper here. But today I will talk to you about the application, or at least our particular application, at least, of robotic technology to the construction of a glass vault. And I will move on. So the glass vault is, as you can see here, a glass brick structure assembled using robots. For this project, we employed 2 cooperating robots without the use of any false work or form work. So I was very interested by a lot of the things Philippe was saying. We've taken a slightly different approach, and I'm sure there'll be many different discussions throughout the day, which I'm really looking forward to hearing. It is an exploration, we think, on the potential of robotic construction for complex masonry structures. The project was a collaboration between SOM, Princeton University, and a number of other academic and construction partners, which I will talk to you about later on. And now, whilst robots did a significant amount of work, humans are also heavily involved, but I think we can all imagine that in the future there may well be a different all-robot scenario beyond these sort of more researchy type projects. In the order to place the Glass Vault project in the proper context, I'll just start with a brief journey through the SOM structural exhibitions. For a number of years, since January 2016, in fact, we have put on these travelling exhibitions. The first was set up at the Architecture Gallery in Munich and started with a fairly simple and small showcasing at the back of a bookshop, showcasing the research work conducted with the SOM Structural Group. And this small exhibit was primarily put on to accompany the release of Detail 4, which was an expose or a discussion piece, if you like, into the work of the SOM Structures Group. These exhibitions have grown in time, and as can possibly be seen in some of these images here, and these few slides, become larger and more expansive. And they've presented us each time with new opportunities to highlight some of the work that we've done in tower technology, post-tensioning work, and other types of research and design. And in this slide, we can see some of the latest technologies and research in design and construction conducted at SOM. The robotic glass vault in the image in the middle top there represents the most recent example of the design showcasing futuristic construction technologies. And it was built and displayed at the Ambika P3 Gallery at Westminster University in London. The installation was completed in the early part of 2020, just prior to the pandemic. To add further context to these vaulted structures, which Philippe also mentioned, I'm just going to go back a few years. There is a little bit of history behind our research into vaulted elements. We've been collaborating with the Timbrel Vault Workshop and the University of Alcalá in Madrid for a number of years. Here we can see some small scale tests conducted where we were experimenting with the use of reinforcement within the inner and outer leaves of the masonry. This is also about the time we started exploring ideas around machine learning to predict damage and crack development. some fairly obvious damage in some of these elements here. This is a technology that obviously has great potential for the use and assessment of structures in post-disaster situations, but that's a whole other presentation that I'm probably not equipped to present. So sticking with the idea of vaults and compression structures, during these Timbrel vault workshops, we also looked at the ideas of topology optimization to remove material from zones with the least amount of stresses within the vault. And of course, hopefully this plays okay, but there is nothing better than doing some research and then breaking things that we've made. And here's an example of the difference in the performance of a reinforced and an unreinforced vault. It's quite a quick little video, sorry for that. And all of that collaboration resulted in the construction of this quite large 5-meter square freestanding Timbrel vault showcased at the Madrid exhibit in 2019. This was a vault built by very traditional masons, but with obviously a freestanding structure, not imposed into a roof or really to take any major loads, but certainly the structure is quite a stiff element, built with very simple freeform guides to help the masons to build the structure in the shape defined. Now, timber vaults are very efficient. We know this, shell structures that have the additional benefit of being self-supporting. And as I said, they often built without the use of formwork, but in this case, there was simple guides used to define the shape. And this is just an example of some of the topology optimization and the analysis that we undertook to achieve that shape and that form. But when it came to our next exhibit in London, we decided to go a bit further, and we based on the previous experience with the timber vault, we set ourselves some objectives to follow in the glass vault design. So firstly, we wanted the construction to be automated. So we decided that robotics would be potentially the way to go. And we managed to find a supplier who loaned us some heavy duty robots that had actually come off a slave line in a BMW plant in Colorado, and they'd been refurbished. So that was quite a fortuitous alignment. The second objective was to build a vault without formwork, but also without the visual guides that were used by the masons in the Timbrel vault that I just showed. We wanted to be completely form-free this time. We also wanted to use standard bricks, one size, without the need for any custom bricks or special shapes or anything that had to be fabricated specially and brought in. So that was a key driver for this project. And finally, we were looking for a minimal and well-behaved structural shell that primarily is a compression-only structure under gravity loads. So we used a form-finding method based on the area stress function to find that compression-only form. And in the assembly approach, we were also inspired by ancient barrel vault techniques from the Byzantine era. We ended up using a construction approach similar to the one on the right, which relied on inclined courses of bricks layered against the vertical end wall to construct the vault without formwork. Now, we're obviously starting without a vertical wall in our particular application, but essentially the form is constructed as a series of arches leaning against each other as you move away from the vertical wall in this image on the right. This approach guarantees stability throughout the construction process at each step of the assembly. So I'm going to show you now how we applied that to our particular vault. The form finding process, as I said before, uses the area stress function approach, which requires the definition of states of self-stress satisfying certain requirements. Each state of self-stress defines a planar self-equilibrated system of forces in the shell, which is studied using graphic statics. The image on the left shows the form diagram and force diagram used for the glass vault. And after the definition of the form and force diagram, the area stress function can be calculated and the 3D form of the vault is derived from that function. And there are other components which describe that form based around the robotics, and we'll talk a little bit about that, about the design space, which also helped inform that shape as well. So you might now ask, why did we use glass blocks? We drew inspiration from this beautiful sculpture, Kualala, by artist Pei White at the 2017 Venice Biennale, with this undulating wall of clear and coloured bricks supplied by Poesia. Incidentally, the same group that offered us bricks for our vault as well. And glass is not typically used as a structural element, but however, it does have a high compressive capacity. Also, the relatively high cost of the material, we think, further emphasizes the precision of the robotic fabrication, in that the entire structure could be built without material waste. We also had the opportunity to use clear cast and recycled cut bricks. The recycled cut bricks were a great idea, but unfortunately, the tolerances in the recycled components weren't quite good enough for the repeatability and the necessary tolerances that were required for the precise robotic movements. Now, although there are tolerances in the robotic process, they are much tighter and more aligned to the formed clear cast units on the left side there. So they were chosen given the tolerances that we could achieve using the robotic process. And with the help of the Glass and Transparency Research Group at the Technical University of Delft, we compared the advantage and disadvantages of mechanical versus adhesive connections as well. A dry assembly of interlocking glass components would probably allow the structure to be assembled and disassembled without any joint material, and would allow for that demountability that Philippe just mentioned, but it would have probably saved material and waste. However, to achieve a vault with a complex geometry, several special glass pieces would have been required and would have needed to be cast. And this was A, not economically feasible, but also B, was not in line with one of our driving goals of the project, which was the use of standardized components. So we settled on actually using a two-part rigid epoxy prepared by human operatives during the process. And for the larger gaps, we actually filled in some of the spaces with small acrylic pieces, just to save on the amount of epoxy that was used to fill those joints. And after defining the form of the vault, we studied various tessellation patterns for the brick placement. We ultimately selected a herringbone pattern, which allowed the bricks to naturally lock together to ensure a higher structural stability. The aim was to use one size of block, which was largely the case, but as the standard glass brick sizes were a full and half brick, we were able to utilize both to get a very nice tessellation. And it's a little bit hard to see here on this image on the right, but there are what we call reset planes. Because of the double curvature of this form, there was gaps would have opened up to a quite large degree unless we use these reset planes. So that was a key feature of the tessellation process. To numerically study the equilibrium of the glass vault during all phases of construction, we adopted an iterative procedure based on the limit state analysis and the discrete element method. This analysis allows us to study the stability of the vault at each stage of construction. And here in the image on the left shows the stage construction sequence right through all major stages of the central arch of the vault. And the image on the right shows a few steps of the construction sequence analyzed using the 3DEC software. And that work was carried out by some PhD students and other collaborators at the University of Bergamo. Now, there are obviously a lot of potentials for the utilization of robotic technology in construction. Automation of repetitive manual activities and placement precision are probably the most obvious advantages. However, there are also advantages to construction of spanning structures like this arch, and particularly if we adopt a collaborative robotic assembly strategy. If one robot acts as a support while the other robot places a new brick, as you can clearly see in this image here, then the arch can be built without formwork. The first part constructed for the glass vault was this central arch, as you see here, where the coordination of the robotic efforts was paramount. And we specifically used the robotic setup, as I sort of alluded to before, to identify and visualize the design space that spans between the two robots. And this helped to form not only the logical construction sequence, but also helped to inform the shape of the arch. You can imagine when the arms are being used to place a brick, the shape and geometry of that structure of the actual physical robot could have impacted the shape of the arch. So the actual shape of the arch was informed by the movement and the path dependency of the robots and the place of the brick placement. So it was a very interesting process to think about and include in the design, the form finding techniques. And this whole process ended up as indicated here. First, the robots collaboratively built the central arch that serves as the backbone of the vault. And afterwards, each robot continues the assembly individually on each side of the arch, building out towards themselves. Firstly, when the wall is quite slim, they served as a support to counteract the forces applied to the arch from the opposite side. And then eventually, when the vault had attained sufficient stiffness, the robots were able to more or less build their own parts towards themselves at the same time, thus speeding up the construction process and allowing a fluency there of brick addition. All the design and construction aspects of the vault were validated through physical testing, from material connection tests and brickwork patterns to robotic reach, path planning and sequencing. And these prototypes started quite small, as can be seen here in the images on the left, and increased in size and scope. And eventually we built a full-scale prototype of half the vault at Princeton University, as can be seen in the top right. And then the more or less full vault can be seen in the bottom right picture at the London exhibit. And the constant feedback between the physical testing and design allowed us to change, adapt, improve continuously the makeup of the different sites, robotic setups and other constraints, whether it was sequence, path planning, connection material. All these adjustments were crucial to the success of the project. And after successfully building the vault prototypes at the Princeton University and at other places in the UK prior to full setup at the Ambika Gallery, we proceeded with the final construction here in London. And so there's a quick sequence of images here, which I'll just skip through. The vault on its stage at the Ambika Gallery, pretty much complete there. Beautiful image from the side. You can see this tessellation pattern, and it's sort of obvious or semi-obvious to see the reset planes, which I'm just going to draw on the screen now, just kind of somewhere there. And I would say, let me just, sorry, stop that. I would say that one of the most meaningful outcomes of the project was the way we achieved deeper understanding of the capacity and potential uses of robotic technology. Let's clear that line. And also we gained a clear insight into, I think, how new technologies can have a way of shaping our thinking about design and construction and potentially bring new forms of architecture. This is a range of collaborators. Global Robots were the people that supplied our robots, as I said. And there was a great collaboration with the Form Finding Lab at Princeton. And now I think I have enough time. I'm going to skip through and play a little time-lapse video here, and I'll just talk over this. And I guess at this point, this being near the end of the presentation, if anyone would like to raise their hand and ask a question, we can continue with that. But you can see here the process. The process involves obviously each of the robots going to a very defined place in space. There was 4 setups where the bricks were placed. The robots would grab brick, move it to the right space, and hold it there while the human operatives would apply the epoxy. Now, clearly in the future, we can potentially see space beyond this current setup, this current phase where potentially robots are even taken out of the frame. But at this stage, due to time constraints and cost and obviously research levels and the abilities that we currently have at the moment, we felt that obviously using the epoxy glued brick components was the best and fastest way to achieve what we wanted to achieve. These robots are obviously designed to go a lot faster than we were applying them here, because we had human operatives running around, so they were very, very much controlled and used in a very safe way. But at the end, I think you'll see that the shape of this arch and the beauty of the product and the form that was very totally aligned to this collaborative approach of the robots is something that we felt was very beautiful and certainly an interesting step in the movement towards a very slimline, I guess, process of construction, which uses a minimum amount of material, which is certainly key to the work that we try to do at SOM, as well as new processes to do with additive manufacturing. So thank you for listening. I think I've gone just on time and a few minutes left for a discussion.
Thank you very much, Stuart. Yeah, really amazing presentation. What I really loved is that, you know, your glass product could easily be replaced by other materials. So
absolutely,
this is something really exciting. I have a question. As you showed, we're seeing this really big increase in the adoption of automation in construction and collaboration with robotics. As somebody who's actually working in industry, how do you see this being adopted in the future in the construction side?
Yeah, that's a really good question. I know at SOM we do quite a few artistic installations. But I guess we're predominantly known for large commercial towers, and you know, I would have to say that the construction industry of those sorts of buildings is probably some considerable way behind many other industries. I think of the automotive industry, which has obviously utilized you know, robotic technology much more deeply than say we have. So the construction industry, for the mainstream structures which most people are familiar with, is still some considerable way behind these other industries. But slowly but surely, we are seeing the implementation of robotics into constructions. There is a group, Langer Rourke, who many of you may or may not be familiar with, but they have a fairly amazing factory up at Warsaw in in the Midlands, the north of England, where there is a highly mechanized process for everything from making fabric rebar to setting up formwork to installing the concrete on shake table, etc. So there is very much a process there which uses a range of technologies to bring materials in one end of a factory, and out the other end of the factory becomes a product. So there are some companies that are sort of more moving to the cutting edge, but obviously the style of structures that most people are familiar with have to be, you know, there's a geometry and various constraints, and obviously cost constraints to do with those structures. But we can also see that the use of robotics to continue a drive towards health and safety on site is certainly something that is some of the contractors we're working with looking towards, minimizing the number of laborers on site. It is well known in the industry that anything that can be done off-site obviously saves insurance costs and is obviously faster and more efficient. And so it's a hard question to answer in the sense that there is not much robotic technology on site right now, but I can see a time when certain projects would definitely use robotic technology in a much more holistic way.
Okay. Thank you. Yeah, as we'll see later on in the team, we have quite a few nice examples of this, but I'll pass the ball to Uli.
Yeah, and Stuart, you're also combining this with a high complex and difficult material glass in construction as well. And but on the other side, you're talking to Phaedra and Thalessa from Delft, which are promoting this working with glass bricks very well. So say their projects are still niche projects, but we see that this is an approaching field. And when I see this, I see a clear link to also that glass community, which is active. Thanks for this.